Welcome everyone to the June general meeting of the Kalamazoo Astronomical Society. Last month we were kind of chilly in here, and now it's somewhat comfortable in here, although I've been running around getting set up. I'm a little hot and sweaty, and you can see I'm wearing shorts tonight. I hope everyone doesn't get crazy from my nice hairy legs. And you know, I've been to a lot of star parties with members, and you know, especially Jack and some other folks that aren't with us anymore. And I gotta say, I've never seen a couple of our members in shorts ever. I've never seen Jack in shorts, and I've never seen Sinclair in shorts. I'll show you the closest I ever came to seeing Sinclair in shorts. He's not here to appreciate this, but maybe he'll watch this later. So we'll see if I can share my screen here. We might have to clear this out of the way. I don't know if you can see that. It's there. That's his screen. Let me stop sharing altogether. That might be better. Okay, so we're still sharing there. Best pictures I have of Jack are sleeping. So there he goes. That's it's a little bright in here still, but that's Sinclair at the 2001 Starfest. You can see he does have shorts on, but he has like long johns on too. So that's the closest I've ever come to seeing Sinclair in shorts.
Is there a way to turn down the lights in the front row?
We will. Yep. We
Okay.
will. We won't bother with it now. Not yet. Not yet. Thank you. We'll do that during the presentation. You can view the recording later if you want to see Mike in his long johns with shorts over him. Of course, he'll walk in and everyone's going to start laughing at him. He's not going to know why. So that's all my fault. All right. I do want to begin with the president's report. Now that we're past the comedy routine. The good news is the Eclipse Series grant has been approved in full. We got every dime we asked for. And I know someone's going to ask how much, but because we're recording, I can't say. That would violate the terms of the grant. So if you're really, really curious and you want to see the letter that we got from the Gilmore Foundation approving the grant, I can pass that around in case you're curious. So there we go. And you can double check the terms and make sure I didn't just violate something, get us in trouble. So we should be okay there. So I'll have, of course, more on that in the months to come. We got plenty of time to prepare, which is why I kind of busted a gut getting the grant ready as early as I did. So we're going to have fantastic speakers, talks and workshops between November and March, starting this year into next year. And then again, the biggest part of the grant is for me to go to at least 30 libraries at no charge to them, except for a little bit of gas coverage, and giving Eclipse talks like I did back in 2017, because that worked out really, really well. I got gobs of email from people that came to the library talks saying, I wasn't going to go until I saw your talk and I decided to go, and I love you for it and all that sort of thing. So let's hope it works as well as it did last time. So we're picking up speed here on our eclipse preparation, which includes eclipse shades. Hopefully everyone got the email this morning about the eclipse shades now on sale. They actually been on the website for a little while, but we haven't gotten any sales until today. There's 6 different sales that we got from members around the country today. But of course, I can't do anything with those because we don't get the eclipse shades until Tuesday. Any good Star Trek fan knows everything arrives on a Tuesday. If you don't know what I'm talking about, then you're not a Star Trek fan. So when you do buy your eclipse shades, I was gonna, I could do that here. See if I can do that. Might take a second. So if you haven't looked at the email yet, let me show you what they look like. Of course, maybe we will have to. This is a bright picture, and We're still looking at our speakers just screen, so. I don't know if I can make that any bigger. There we go. That's a little better. So that's what it looks like. They are a little bit different than we had last time. Last time, the eclipse part here went off the screen. You didn't really see the rim of the moon or the edge of the sun there. That was being sort of prominent, so you can see better. But I had to redo it a bit because they weren't happy this time around with the way they were cut. And so we ordered another 2,000 pair, which we did last time too, and sold them out with plenty of time to spare. And last time, we ordered 2,000 and they sent us 2,200, but they said, because we printed an extra 200, we'll give you a discount. This time they emailed me and said, oh, we made 2,100 and we charged you the full rate for the extra. I'm like, yeah, right, you are. So I emailed them the invoice from last time where they gave us the discount for the extra, and they said, okay, we'll knock 15% off the extra 100. I'm like, well, yeah, you will. You're going to, or you're going to pulp them. So, I think they got a little scam going on there. So if anyone has to order eclipse shades for another group, make sure you say, I want 2,000 exactly. No more, no less. Unless you want a couple hundred more, maybe. Don't say that, and then you can get them at a discount. So there you go. And we're doing something a little different than most other places that sell eclipse shades. It's something that we did 6-7 years ago. Is with each pair you buy, you get this 4x6 postcard inside a very nice resealable bag. It's not a Ziploc bag. We'll get sued if we call them Ziploc bags because they're not Ziploc bags. And on the back, they have all kinds of lovely information about the 2024 eclipse and how to check your eclipse shades for those that might not know any better. Well, there's a gaping hole in it. Are they safe to use? And this is no one here. If light comes through, they're not safe to use. So if you want a postcard, $3. Even if you don't want the eclipse shade, still $3. Let's see, we're doing really good on the volunteer positions. For the past 2 months, I've been looking for volunteers for positions we have available. And first, I want to thank Arya Jayatilaka for serving as the equipment manager for over 8 years. So Arya started back in right toward the end of December in 2014, and he finished up this past last month in May. And we want to thank Arya for his many years of service. It's not a demanding job, but still, it's a very important position. And we do want to welcome aboard our new equipment manager, someone most people know, and it's Joe Comiskey. So thank you very much, Joe. So if you want to check out our short tube 80, our PST, our Celestar 8, the 20x100 or 25x100 binoculars, I forget which. And we also have the ZWO ASI 294 CMOS camera, which you can't have because I have that at my house. And of course, I don't use it very much lately, but it's mine. But that's all available for checkout. And so if you do contact the equipment manager through the contact form, because I don't know if anyone noticed, we took off all the email addresses off the website because everyone on the board kept getting emails from someone posing as me saying, we're in distress, I'm in distress, send me 10 grand right now and everything will be fine. And so we just finally got sick of those and finally had to do away with all the email addresses on the website. So now you have to go through the contact form, and I'll forward it off to the person that you want to contact. And so if it's Joe, yes.
So that's how they get my email.
Yeah. Yeah, I'll forward the contact form to you when someone contacts you, because there's a pop-up and you can select who you want to contact. And then if it's you, it goes to me.
My email or phone is not up.
Yeah, no, you definitely don't want to put your phone number on there, because then you'll get called from UFO people like Sinclair did back when he was president. And if you get your email on there, you'll get emails from people posing as me saying I need $100,000 now or else. And so,
Wow, that's good.
so yeah, that's life on the internet. And we do have some library telescope coordinators. Of course, Mike Cook started the library telescope program several years back, and now Steve Crawford and Patricia Guilford have volunteered to help him out with the library telescope program. Of course, we can always use more volunteers with the library telescope program. So if you were afraid to volunteer because you thought you'd be all by yourself, nope, there are 3 people currently doing it. So, you know, the more people we have, maybe the more the program can spread to other libraries, you know. One thing I could do as I go to all these libraries is give them a little forum that someone can make that we can say, hey, we can set up this telescope for you, and there we go. So that's a great opportunity to do something like that. As you may have read in the newsletter, if you looked at it yet, we did some OWL observatory maintenance already on May 22nd. So Dave Garden was out there, of course, because we definitely need Dave. New member who just took training, Walter Glogowski. I'll work on that. Again, he's a relatively new member from South Haven. Jack Price was there, the masked man himself. Don Stillwell and Dave Wolf were all there. And I guess what we talked about at the meeting didn't quite go the way I thought, because I thought they were just going to replace the boards and fill the holes for staining next time. But sounds like they just cleaned the interior, which is what I thought we were going to do next time. So the interior is nice and clean now. All the dead bugs and cobwebs are gone. They got the rock bed weeded. It's probably bad already because they grow like weeds, you know. And then Jack repaired the fan because apparently Mumbauer didn't wire it up as well as we thought.
I don't know that we're gonna blame Pete completely on.
No, I'm blaming Pete completely.
I think there's some guilt back here in this row on how it's, yeah, we'll talk about that later.
Okay. Well, you're here. He's not. I'm blaming Pete. It's all his fault. It's completely 100% his fault. And then Sunday I'll talk about what we're supposed to do. But now we're mainly at least Dave Garden and Don Stillwell. They're going to replace the fuchsia boards or whatever the hell they're called. Fascia. I knew I was going to screw that up. And fill the woodpecker holes because they're little pecking a storm up there. And then we're going to restain the exterior. I did buy all the stain. I got the brushes and the pans and all that sort of thing. So I'm ready to go there. But, you know, the high Sunday is again going to be 86. Just hang on to it now. And is it going to be too hot to do it on Sunday? Do you guys want to work out there at high noon or 1 o'clock on Sunday? And or should we wait like a week or so and delay when it's going to be a little cooler? Okay. Well, we have a long-standing policy that people not die at club activities, including maintenance. So we do. Observatories aren't known for their shady spaces, so I don't know. Okay, well, okay, so we'll go ahead and go with 1 o'clock. Bring a towel. You know, don't forget to bring a towel. If you're not a South Park fan, you have no idea what I'm talking about. Bring a towel, bring lots of water, and when you run out of water, just wring the sweat into the water jug and you can drink that. So if Mumbauer were there, he would start one of his water fights like it did at the 95 picnic when it was 112 degrees. So it wasn't, that was much worse. But we were sitting down back then and we were in the shade. Okay, so we'll go ahead with this Sunday, June 4th at 1 o'clock, although again, Don and Dave will be there at 9 a.m. Replacing the fascia boards or whatever the hell they're called. Another screen share. Let's see if I can do this, just because I'm going to ramble off a bunch of dates and you're probably going to forget what I say. But we have a lot of community outreach coming up. We're going to do, as you can see, Space Camp at the Air Zoo on Monday, June 19th from 1:15 to 2:15. It probably won't go quite that long. We'll probably get there about 1 or a little earlier. And they're usually out there for maybe 30, 35 minutes or so. And, you know, so we look at the sun, at white light and H alpha, and there's roughly 25, 30 space campers. And they're all usually really good kids. We don't usually have any trouble with them. So I know I'll do it. I usually do that because it's some, you know, fun, educational. And I'm pretty sure that Jeremiah said that he was going to do it too, but you know, there's always room for other people to with other different scopes to look through. And then we got invited back to Pierce Cedar Creek again. We did that last year, and it was okay. It wasn't terribly busy, but they're having family science night again. Pierce Cedar Creek is out by kind of a little past Delton. Yeah, Cloverdale. Yeah, it's closer to Delton, I think. And that'll be on, I think June 21st is the solstice this year. So we'll be out there on the first day of summer. And I told them, because last year we did hands-on and solar viewing, but I don't know, you know, it wasn't terribly busy. So I figured we just focus on solar viewing, and we'll have the eclipse shades by then, so we can sell eclipse shades. But I doubt we'll move that many because it'll be pretty quiet. And so I can probably handle that one by myself. But again, it's always good to have at least 2 people there, you know, so someone can maybe run off and get out of the sun for a bit and get some water, cool off and that sort of thing. So, you know, if anybody wants to help out at Pierce Cedar Creek, that'd be great. The one that might be kind of busy is the Space STEAM Day at the Air Zoo on Saturday, June 24th from about 10 a.m. to 2 p.m. We're definitely doing solar observing. But again, we need at least 2 people inside to do a hands-on activity if we do one, but you know, they might have a good enough crowd to do one. And then we need maybe another table to pass out KS literature and stuff like that. We can't really sell eclipse shades because they have their own there. I don't know if they're selling them or they're giving them away, but either way, we can't compete with them in that regard. So if we just do solar observing, that's good enough, but it would be nice to have somebody inside passing out at least KS literature. I'm not too terribly dedicated to doing the hands-on thing. I've been doing hands-on stuff since, geez, I don't know what, Eric, 1987 or something like that, 1988, since the early days at the museum. So I've done plenty of hands-on stuff. I've had my fill of it for one lifetime. But again, it's fun to do. Just after 30 years, you don't get too excited about it anymore. Then at least Jack and company will be at the Kindleberger Festival in Kindleberger Park in Parchment on Saturday, July 15th this year. We will be selling eclipse shades there. We usually at least pass out KS literature, NASA freebies, and anything else.
Maybe do the maybe eclipses again or something.
The baby black holes, you mean? Okay, well, I think we'll have to order more of those, right? Because Don, you're pretty much cleaned out of those.
Yeah, we have to order the parts because we're not done with the bridges.
Well, if we get enough new NASA handouts, we can probably just do that stuff.
Okay.
There's those other couple of possibilities within solar system. The tape.
Yeah, but it's nice to have, you know, there's that, but I don't know, it's, you look at it once and you throw it away. Like a planisphere, at least you can use it for something, and or a Big Dipper clock, or yeah, I think we need to make copies of those too.
That's always a good time. And Kindleberger decided to throw me a birthday party this year, but I haven't had my birthday, so.
Right. So Jack will definitely need help with that. And then we're going to be at the Parchment Community Library. That's what PCL stands for. We're just going to observe the sun. This is something that Karen Woodworth has set up. So we'll do that from 11 to 12 at 12:30. Again, I think just like 2 members will be good enough for that. But again, more the merrier. So, you know, these aren't labor intensive. You just got to come, share at least views of the sun, maybe pass out some brochures, and there you go. So that is our outreach. And we haven't seen, for the past couple of years, Andrew Lovelace has done the grilling for the Perseid Potluck Picnic. So, you know, 2 years in a row is pretty good. So the Perseid Potluck Picnic, I didn't put it on here, but I think it's August 5th this year. Yeah. So we're going to be back at Van Buren State Park for that. Cross your fingers that the weather will be better this time. Last year it was pretty chilly. But do we have any volunteers to maybe bring a grill and do the cooking this year? Anybody want to give Andrew a break? He'd probably do it if I ask him, but you know, if we don't get anybody here, we can send out an email to everyone and see if we can find somebody else. But it'd be nice if it was somebody that was here, one of you deadbeats. All right, we'll keep looking. Or if you want to think about it, go right ahead. All right, so without further ado, let's go ahead and introduce our speaker. So tonight's guest speaker last visited us in June of 2014, exactly 9 years ago. I don't think it was on the 2nd, but nine years ago. But that meeting was held at the Kalamazoo Nature Center, and this is his first time joining us at our regular site here at the Kalamazoo Area Math and Science Center. He is now a Professor Emeritus in the Department of Earth and Environmental Sciences at Michigan State University, and a former research associate in the Division of Meteorites at the Smithsonian Institution. His research investigates the geological, mineralogical, geochemical, and geomorphic factors that control mineral alterations at Earth's surface, including distinguishing the effects of terrestrial weathering and Martian weathering on Mars meteorites to better understand the geological history of surface processes on Mars. He is currently a member of the International Mars Sample Return Campaign Science Group, a joint NASA and European Space Agency charged with establishing protocols for receiving, curating, and managing Martian samples after their arrival at Earth in the early 2030s. And if we ask him back, maybe in the 2040s, he'll have samples from Mars to pass out to us. So we're looking forward to that. So without further ado, please welcome back Dr. Michael Velbel. Thank you.
Thank you. Thank you, Richard.
Now we can bring the lights down.
All right. Well, thank you for inviting me back. It is a treat to be here. Now, let's see if we got this bug work down here. So now I'm sharing this one, right?
I believe so.
So far, so good?
That looks good.
Yep, that's going to move. All right. So thank you for the introduction. That's me. I'm going to be passing out props here for a moment. You'll see the connection eventually. I'm going to do what we used to do in class when I used to teach. I'm going to come up the aisle and please pass things down the row. One per.
Sorry,
two.
nobody at home gets any treats.
Yeah.
Supply your own treats at home,
There are
please.
plenty of extras. I can toss them to you to play catch. Is the microphone on, or is there something I'm supposed to do to it, or I have the switch. I'm going to come through here.
Thank you.
All right.
Whatever it is.
But this is just like teaching used to be, except, oh, never mind. Take one, pass them on. You'll see the connection in a minute here. So we want to be clear here. You know, the short version of the Enterprise is life on Mars, but no one expects active, viable life on Mars under Mars's current conditions. So, oops, sorry. So the search starts sort of where a geologist would start. Oh, you got, oh, that's right. Good work, thank you. All right. If there isn't life now, that's too bad in some ways. But what if there might have been at some time in Mars's geologic past? And where would we look? And we'll see in a moment, we'll talk about that. But the search is not to look for something we have real reasons not to expect. Thin atmosphere, ultraviolet radiation. It's nasty to reduced carbon compounds, so-called organic molecules that are on the surface of Mars that come in as part of the tarry matter in carbonaceous chondrites that fall on Mars. The ultraviolet breaks up a lot of stuff, and no one expects things to survive there under the present circumstances. But Mars hasn't always been like that. And that's why the farther back we go, the more evidence we find that there may very well have been atmospheric pressures high enough for liquid water at the surface and so forth. So The search for life on Mars immediately has the parenthetical statement built in, specifically ancient microbial at best. We're not looking for seashells. We're not expecting body fossils of any kind. We know that there's evidence for ancient microbial life on Earth in some of Earth's oldest surviving rocks. So the one thing that we might find would be evidence of ancient microbial life. And the mission that's up there now, or the most recent one that's up there now, Perseverance, is the latest and somewhere near culminating step in having this happen. A brief history of human understanding of Mars until the decade that I was born, basically. Mars was entirely the province of astronomers. Everything we knew about Mars, we knew about the ultimate remote sensing Earth-based telescopes and the observations they could make. The unaided eye could tell us about dynamics and some things about orbits and so forth. And we've all heard the story of perceptual enthusiasm on the part of Percival Lowell. You know, this is what the rest of us saw. Somehow he saw that. In the 60s, spacecraft began being sent to Mars. There's a sort of a hierarchy of sophistication and complexity in doing this. Normally, one starts with something really simple, like a flyby. You don't even bother about knowing enough about the mass of the target to calculate an orbit. You just go fly by it, take pictures, do some spectroscopic measurements, measure how much the trajectory is deflected, and finally get a better sense of the mass. And there were flyby and orbiter missions around Mars. Several Mariner series spacecraft. Early ones were flybys, later ones were orbital. All of this began in earnest in several ways, including for me personally, because I was old enough to know what was going on by the time, when Viking landed on Mars. Actually, Viking didn't just land. There were two pairs of Viking spacecraft, each two orbiters and two landers, went for the gusto. And the one of the spacecraft lasted 6 years. So from 1976, the last one of them stopped functioning in 1982. So orbital imagery, orbital data, in particular, were continuing to come in and gave us a very much better understanding of what to look at on the surface of Mars, what to look for and think about. And all of this imaging the surface from orbit, even before Viking, all of this began the transition of Mars from an object that was studied only by astronomers to an object that geologists would study too. First and foremost, the landforms on Mars, volcanoes, canals, canyons. Geologists study those things. Subsequent orbiters in particular increased spectroscopic capabilities, and thank goodness this is an astronomy association, because you know what spectroscopy is. We'll save 15 minutes right there of the talk. Various wavelength ranges and so forth to detect different sorts of phenomena on the surface of Mars, including, if not specific minerals, then at least frequencies of vibrations that are associated with specific kinds of chemical bonds that only occur in certain kinds of minerals. Also dynamic features, seasonal features on Mars. One could fly over with an orbiter, one could fly over the same place and see some of the changes from season to season. There were also landers, although the history of landers is a little bit more erratic. The two Viking landers landed on two different parts of Mars and built up a lot of expectations that they were going to provide a definitive answer as to the question whether there was current life on Mars, microbial survivors of some sort. Of course, the first answer was, oh my gosh, the chemicals in the reaction vessels are changing. The second answer was they're supposed to keep changing, and they stopped really quickly. And after a few months of thinking about it, it appeared that the surface of Mars was way more oxidizing than people thought, and that it was basically peroxide compounds decomposing the organic matter, not microbes respiring them. Okay. So there's a National Academy of Science report. There are a number of them. The National Academy and its Space Science Board often contribute wisdom based on experience and perception of how to understand things that are going on. There's a National Academy of Science report. Anybody's interested, email me. I'll look it up and send it to you. That there's about 2 paragraphs in it where you don't have to read between the lines too hard to read them saying pretty clearly that NASA got really cold feet after 1976, and the blowback of, you spent how much to find life on Mars and you found what? Resulted in a 21-year gap until the next surface mission, Pathfinder. Now, it takes a long time to plan these things, so it's not like in 1996, they suddenly decided they were going to send Pathfinder. That was in the middle for several years before that. More orbiters, more landers and rovers. Orbiters give you the wide-angle view from above. Rovers, landers can operate only in their restricted areas. The rovers can move around a little bit. We build up knowledge. The community tries more sophisticated things. Initially, a task was, follow the water, find the evidence of water. This is a fracture network. There are some beautiful images of dendritic tree-like river systems from orbit. The gullies, is there water running down them once in a while or not? Or are they relics from the past? We've learned something new from each mission. And this eventually brings us to the state of knowledge where the community got pretty good at finding evidence of water. You find you think from orbit, this is a place you should look to find evidence of ancient water. You get there, you find chemical evidence in the minerals of ancient water. So far, so good. Follow the water worked. Next thing is, of all the places that have water, which places are potentially habitable? Some places aren't. Some places are. So Curiosity, Mars Science Laboratory, nailed it. They anticipated from what they learned from previous landed missions and from orbital data that the place that they chose for Curiosity to land was a potential habitable environment. They landed, they found lots of evidence of lake deposits. Things like to live in lakes on Earth. All right, the deposits are very ancient, but the contract for zeroing in on the habitability. Having proven that we can find at least potentially habitable environments on Mars, the job of Perseverance was to say, okay, now let's try to find out if something inhabited it. And let's look for the actual evidence of life on Mars. Every spacecraft is limited by a number of things. The fundamental one is money. All right, that's always a big constraint. How much do things weigh? You can only put so much payload on the top of a rocket that costs a certain number of hundreds of millions of dollars. So you have to choose. You can't send every possible instrument each time. And you can only send instruments that will fit on the spacecraft. And you don't want to send one big instrument because that's not a great idea. A typical spacecraft has about 5 to 10 smaller instruments. Sometimes you can miniaturize things. The payloads have certain things in common from one mission to the next, certain kinds of spectroscopic X-ray chemistry. Instruments are pretty much on every single lander or rover you've heard of, except Phoenix didn't have one. And then there are some things that only appear once in a while. This is the first ultraviolet Raman spectrometer to be put on another planet. There have been different kinds of spectrometers. There are always cameras, and there's always visible and near infrared spectroscopy or photometry somehow capable from the cameras. So elemental abundances of about 2/3 of the periodic table, spectroscopic properties over certain wavelength ranges that apply to both minerals and certain organic compounds. This is the weather station, 2 different kinds of cameras and photometry. And on this one, the first NASA mission with one of these to Mars, ground penetrating radar. So they can get a little bit of sense of what is going on a few tens of meters into the subsurface, not just taking pictures of the surface. Some of these are primarily for looking at things from a distance. Some of these are for the instruments to be right in contact with the sample or right up close to it, proximity science or contact science. And since this mission is specifically intended to acquire samples that can eventually come back to Earth on a future spacecraft, the robotic arm is also what does all the sample manipulation and drilling and so forth to actually acquire the samples. Okay. The region that was chosen, Jezero crater here, was chosen from among many possible landing sites. It's a little bit like March Madness, the landing site selection process. There might be 60 or 80 research groups each proposing a landing site, and there's a kind of a formal process of presenting it at a workshop and getting the workshop consensus on which ones are worth more thought, and it eventually comes down to a landing site selection process where they're looking at 3 or 4 and deciding which one to recommend to NASA headquarters for spending the amount of money, committing that amount of money to the hardware that's going to go to that place. There are many impact craters on Mars, and quite a few of them, many dozens of them, have evidence even from orbit that one of the channels that comes in across the rim deposited sediment in a delta. Think Mississippi Delta, right? River with sediment in it, dumps into a big body of water, deposits a delta. They had dozens of deltas to choose from. Jezero crater, both for its own internal reasons and because it's so close to some of the geologically oldest terrains on Mars, so that if the spacecraft outlives its warranty and gets its work done and can leave the crater, there's something very different and equally exciting outside the crater to study as well. So here's a geologist's map. We were given colored pencils and crayons in grade school, and we just never got over it. You draw colors on the map. The crater floor. Now remember, we're going to talk about discovering certain things, but it's not like we didn't have reasons to expect certain things either. The spectroscopy said of this material that it contains the minerals that are common in certain kinds of volcanic rocks on Earth, like the iron, magnesium-rich ones, think like the Hawaiian Islands. But it doesn't necessarily mean they had to be lavas. They could have been volcanic ash. The atmosphere on ancient Mars would allow that gentle magmatic flow that we see at Kilauea. On Mars, the difference in the atmospheric conditions, the gas would like take the lid off a soda jug, 2-liter. It would explode out, and basalt can erupt explosively on Mars, or at least it could under certain sets of atmospheric conditions. So this could have been volcanic ash made up of the same minerals. That would mean something real different than these being, lava flows or something that were at the bottom of the crater. Farther out, even from orbit, there are patterns that look like ancient channels, sinuous channels, as we see that sinuosity, for instance, in the Mississippi Delta. These are the sedimentary rock deposits formed by the ancient delta. Here's the channel where it came in. Then there's a region out here with some minerals in it that are called the bathtub ring. If the delta, the delta is here, it was deposited into a lake where the top of the lake level was basically the top of the delta. So you can tell what the lake level was. And this would have been shallow or at the same level at the same time. Then the rim of the impact crater from before there was any water in the lake, and then the landscape outside. This much, the compositions, what minerals must be in here, the features on the surface that tell us about the sedimentary origins of these materials, that was known at the time of the landing site selection process. The research team that proposed this site had done all their homework. They'd looked at all the orbital data, the orbital imagery, spectroscopy, and so forth. So there's something to do at this site for different specialties. People who care about the origin and the emplacement of igneous materials can study the crater floor. Those of us who are like me were interested in the sediments and the sedimentary rocks, the surface materials, less connected to the interior of the planet. There's stuff for us to study here. There are different relatives of this on the bathtub rim. And then for our planetary geologist colleagues who just like what was the ancient crust like and so forth, many different specialty areas in geology can learn something from this site. So I put words on top of here, the composition of the floor deposits. The deltas on Earth contain clay minerals, and of all the minerals, that make soil and the plastic, the plasticity of them, those are the most likely host for organic molecules. Commercial applications of natural clays on Earth include things like filtration of organic compounds and so forth. It would be interesting to know what's underneath this unit. These are river deposits. They're made up of grains that came from anywhere that where the grain could have been picked up by the river. So individual pieces of gravel and individual pebbles and boulders and things like that in here, individual sand grains in here, tell us something about those kinds of materials having to have been present at the time the river was running in wherever the water could flow into the river. Something for everybody. The spacecraft landed here on this light-toned crater floor unit. It spent a lot of time studying here. So the spacecraft lands. There's a period of several months where they start everything up, make sure each instrument functions, make sure every moving part functions, one at a time. It was several months before they started even doing science. I think it was more than 60 days before it even moved, just as it was flexing its muscles and seeing if all the circuitry and the controls worked. For certain reasons, this rough-looking terrain down here, the roughness, there are two bad kinds of roughness on a surface as far as rovers are concerned. There are boulders. You don't want boulders higher than the axles because you don't want to high center the spacecraft on a boulder trying to get over it. And you don't want small sand dunes because traction in a sand pit of ball bearings, little tiny ball bearings, is ridiculous. I was on a field trip with a geology group a couple weekends ago, and someone carelessly suggested to the bus driver that they should pull over here while we waited for the car convoy behind. The driver asked us to delete all the pictures of getting the truck out of the bus out of the sand. Rovers can't go over a small dune that's even a few tens of centimeters high. That's enough sand that if all six wheels get on it and you start spinning one of them, Spirit never got out. Mars Exploration Rover Spirit didn't get out of a jam like this in time. Excuse me, I didn't realize at first that was me. So that worked well for the igneous community. They studied the edge of this body of igneous, it turned out to be igneous rock, not volcanic ash, and sampled 8 samples, 4 pairs of 2 samples each around here, and then finished there. That was the part of the campaign called the Crater Floor Campaign. In the meantime, though, remember I said earlier that some of the instruments are good for wide angle stuff from a distance. Other hardware is good for getting up close to the stuff you're studying. They're always in use, not exactly simultaneously. Which instruments are using up power today? Which instruments are going to take up a lot of memory? They can't run all the instruments at the same time. There isn't enough power to run them all at the same time. There isn't enough onboard memory to store all the data from all the instruments if they're all running all the time. So there are choices that have to be made. They plan a few days. They plan overall, they know where they are. On a day-to-day basis, they plan about 3 days ahead with last-minute changes based on whatever the data were that came down yesterday. And they send up new commands. So while the spacecraft was exercising, some of the remote instruments, one of the first things they did was to take a 360-degree panorama, very high resolution. It's made up of thousands of individual images, this size, with good resolution at each image. And the panorama from an overlook that was approximately here, they took the 360, but the view we were looking at in the next slide is looking over this way at the eroded edge, the kind of the cliff edge where more resistant rock types on top are holding up the sort of plateau, if you will, and rocks that are more easily eroded, more like shale, are underneath. And this is the edge of the delta. This feature here, I'll come back in a minute, so it's Kodiak, and there are specific scarps holding up the edge of the bluff. And this is Kodiak, and these are some of those scarps at the edge of the bluff. So these were seen from orbit even before they landed. That was part of the background information for landing site selection. And from the ground, you've got your local landscape. You look over the rough landscape you can't drive over, and you look at the edge of the delta, the ancient delta. And that's going on while other instruments are being tested and so forth. This shows the geometry of what we just looked at. Here's the rover down at this edge, and how wide is the field of view at Kodiak? What do you see? You see big, thick 10-meter layers of sedimentary rocks with different kinds of sedimentary structures in them that tell you it was an ancient delta, where a delta built out over layers on the lake floor, built up a lot of sand, and then on top of it, at lake level, were the flat-lying sands. In some places, there are boulder conglomerates. You can see we're looking at about a kilometer away, looking with the zoom. Never intended to get much closer to it, and never intended to collect samples there, but it was a really terrific exposure from a geologist's point of view. And the instrument that takes these pictures is on the mast, and it's a camera, so it has the really imaginative name of mast cam. There was a mast cam on Curiosity. This one can zoom. Curiosities couldn't, so this is mast cam Z. And they can zoom in and get close-up pictures of individual boulders up to 1 meter in size. Okay, at least once in a while, the current in these rivers was really something. This was one of the early pictures, one of the early frames. This is a raw, unprocessed picture. And it was my favorite. I mean, I taught sedimentology at Michigan State for about half of the 39 and a half years that I worked there. So I knew right away what this was. But they have all the detailed data with exactly how do you tell from the picture how thick things are and stuff like that. They did some very, very good work on this. And with more detailed work, they have established several different stages of lake level at different times, at the time of delta formation and so forth. And this particular crater lake, a channel broke through the rim, and a river channel came through here. And there was an outlet. If the water level got high enough, it couldn't get any higher, it would spill out into a channel going the other way. This is fairly common on Mars. It's common in a lot of proglacial lakes on Earth that have nothing to do with craters. It's not a particularly rare thing, but it allows one to say, you know, what's the maximum possible depth? And compared to that, what was the actual depth of the water approximately when the delta was formed? When they finished down here, collected the igneous rocks, everything was working fine. The next thing to do was let's get up closer and start learning more close-up details and start anticipating, figuring out what do we want to collect? What does the community want to collect here? So they hightailed it like this. I have a certain, I didn't specialize in shales, and I retired before I could, I guess. There might have been a long time ago shales here, but there was another set of traction problems. One wouldn't be able to drive on flakes of mudstone. So they drove right past it, and I'm kind of, you know, like looking at the pictures as though I'm a kid looking out the window, you know, driving past the Dairy Queen or something. You know, can we stop? Can't we stop? You know, no. Can't do everything. Can't do everything. So the next campaign, the crater floor campaign, was what they called this, the Delta Front, or sedimentary geologists would call that, Delta Front campaign. A view of some of what was going on there, some of the bigger grain sizes that are more resistant to erosion hold up the edges. There are thinner beds of those along with beds of fine-grained sandstone or siltstone for various reasons of grain size and composition. Sometimes there are bands of different color. This is really a vanishing point thing. These are the same two layers. It's just they're going, you know, far, far away. They were able to get to a few places. They could drive up here of a gentle slope to Skinner Ridge. They could work their way back down, trying to find a place where there's an exposure of what looks like the local rock. It's in place. It hasn't been tumbled around. It hasn't been moved. And those are the places where you know its relationship to other parts of the same layer that you can determine from color and spectroscopy. You can determine from both orbital and ground information how far do those layers extend, how many hundreds of meters or even kilometers. And if you know that you've got an intact, in place piece of one, that's a great thing to sample. And that's what they were going for. The robotic arm had a variety of instruments. First, you have to, a geologist would take a piece of the rock that isn't necessarily the one we want to collect, and we would do something to take whatever rusty, weathered surface might be on it and break it open with a rock hammer and look at something a little bit fresher than the surface that's been exposed for possibly tens of millions of years. Let's look at something a little fresher. What they do on this, both Curiosity, well, no, Curiosity didn't do this, but similarities and differences. What they do on Perseverance is they have a 2 meter diameter, 2 inch diameter, 5 centimeter diameter abrasion disc. And they abrade a 50 millimeter diameter, flat spot. Not polished, just kind of smooth it out a little bit. And that's the first thing that they do. You have the natural surface with whatever dust is on it, whatever oxidation happened right at the surface. You abrade through that and get a slightly fresher surface, roughly a centimeter underneath, maybe a little less, maybe a little more. And then they do all sorts of put the first, they do the abrasion, and then on the abraded surface, they get different kinds of information. They take pictures, they co-register, we'll skip this one. They co-register the data. Let's see, this is the one of the rocks that they chose in this particular case. And eventually, this will be one where they abrade it and decide. I mean, other places they abraded it and said, even abrading it shows how brittle it was. It'll be really hard to drill this. So we're going to not do any more with this locality. Then they go to the next locality. Oh, okay, this one holds together. And it looks like it's similar to the other one in certain important ways. Eventually, they picked this. This is what the surface looked like after they chose it to explore it. Then they created the abraded surface. Not a lot of big grains in there. It's pretty smooth and homogeneous. It's a pretty fine grain, small grain size for what it is. I have a 300 megabyte video that I couldn't fit into the slideshow, and I think rather than get out of the slideshow, try the video and come back in. I think we'll maybe do that in Q&A. I don't want to muck up the tech. In case it comes up in Q&A, another thing, these little bumps, turns out they might be interesting. All right. Okay, this is a miniature version. This demonstrates several different capabilities of the instruments on the robotic arm, all in one slide. The imager, you can just keep bringing the camera closer and closer and refocusing it, and you can get a view of the whole surface, and you can get views down to basically the resolution limit of an optical imaging system. How close can you focus? If you then choose a place and abrade it, the two different kinds of spectrometers, the Raman, the Sherlock instrument, can measure Raman spectra at a number of discrete spots. And this highlights where calcium carbonate and calcium sulfate bonds were detected by the Raman spectroscopy. And that's overlaid on a picture. Each of those spectrometers has its own imaging system, its own camera. So you can co-register where are the interesting spots with certain spectral attributes in relation to just what you can see. And here are the test maps where the X-ray spectroscopy, gamma rays excite electron transitions into different elements in the target material, and then those abundances of them can be detected and mapped again, spatially resolved onto a map. And here again, the different color coding corresponds to things like sulfate minerals, carbonate minerals, and two different rock minerals, in this case of an igneous rock. They do this every time they abrade, and sometimes they say this is the same as we saw before, or there are other reasons for not drilling it. Good, we got some data, we'll store the data, we'll send it back to Earth, we'll move on. Every now and then it's determined that, that we've learned enough that the next thing to do is actually to drill. So here's the abrasion spot on one sedimentary rock, and here they're putting down the drill to actually drill a sample. Now about these drills and this coring, we'll see an example, kind of a stop action video in a moment. The drill part is a drill bit, and it's got the screws, threads at the end. It's a rotary percussion drill. It breaks up the material that's in contact with the drill bit, and the spiral action, the sort of Archimedes pump of the threads, clears out the granular material, the debris, moves it up, and it piles out around the cylindrical hole. In the meantime, it's doing all of this around a roughly chalk-sized. Now is the time for your Mars core analog. The diameter and the length of a pack of Smarties is nearly identical to the design capacity of the tube. They were designed to drill this size. If it's intact, think of it as a piece of chalk. Did I miss you?
No.
Oh, no, okay. Okay, good. Oh, here, have one. That's it. So there it is, pack of Smarties. Right, 6 centimeters long, 60 millimeters long, 0, 50. There's a test core from when they were trying out different specific designs and mechanisms of the drill. So forget 700 pounds of Apollo rocks.
Oh, yeah.
Yeah, we're not talking about anything like that. Okay, fortunately, analytical techniques have improved amazingly since the late 60s. And one can do a tremendous amount of science with a pretty small amount of sample.
Mhm.
All right. So here, there on another rock, here's the patch, the abrasion patch. It was examined by all the spectroscopic techniques. It was determined that this looks like the right kind of material, has the right mineralogy and chemistry to be representative. You have something that kind of, rest one hand over here and operate the drill. And this will cycle through a number of times. And you'll watch the shadows move. This took several hours. Okay, it's not that fast. It's time lapse. So this is basically stabilizing the robot arm against the vibrations. And then you can see the deeper it drills, the more of the stuff around it and in front of the drill bit's crushed up, and it's coming out the sides. And inside that tube is the core. All right. And after abrading it, and in this particular case, later in the mission, acquiring one core, that's what it looks like after. You're done. You've gone through all of the wide angle viewing to decide you're going to drive up to this outcrop, this cliff face. You get up close to different parts of it. You abrade some of the places. You reject some for certain reasons. You accept others and decide to proceed with that being the specific place to collect the sample. Early in the mission, they took 2 at each place. We'll come back with the story of why in a moment. And here again, abrasion patch from a previous step and 2 successive drills. Abrasion patch, 2 successive drills. All right. In this case, these are both outcrops of sedimentary rock where everything else around them, it looks like it may be cracked and stuff like this, but it's all one layer with cracks in it. And we'll take one of the pieces and sample it. Here, this is one of my favorite slides. I studied sediments and sedimentary rocks, among other things. This is one of my favorite. At Skinner Ridge, the upper ridge, where there were more coarse-grained sand and even gravel pebble size. And then Wildcat Ridge was finer grained sediment below. That was the one where you looked at the abrasion patch and it looked kind of uniform and smooth and didn't seem to have much in it. Oh, I managed to set 2 different timers. Anyway, all right. The naming conventions are the team names things, they give them names and then the names stick. So we have 2 samples of sandstone, and in the sandstone we can see big light colored grains, big dark colored grains, intermediate sized grains, a lot of fine grained material in between. Pretty much similar over here. A few tens of centimeters along the same outcrop is where this next drill hole was. And the stuff that abraded, looking pretty homogeneous, looks that way here too. What this is it's the bottom end of the drill core. All right, it drilled created all the powder, got it out of the way. If it needed to be broken off from being attached to the bottom, it did that. And then it extracted the whole thing, and they turned the tube over, and they look in the camera, just take a picture of what the bottom end, that's the only thing they can see. They can't see the side of the core. They can't see the top of the core, except that it's probably the outcrop surface, what it was like before it was abraded, because they drilled outside the abrasion. So, but these are what the rock that actually got into the tubes, at least one end of it, looks like. As part of taking the pictures, they do a couple things, including just a through focus series. They move the camera relative to the drill, and at some point, the surface of the core is in focus, and above that it's not in focus, and below that it's not in focus. They actually don't determine the length of the core that way. They have a probe that gently pushes at the core, and when it meets resistance, they know how far it probed in, and that's the basis for the estimate of how long the core is. It doesn't mean it's intact. It could be like the Skittles, the Smarties. I mean, it could have broken, and just that's as closely as it packs. So we don't know for sure. And then after it is established that there's a core in there, they didn't establish that the first time. That's its own little story. Then it is sealed up. The end of the tube is sealed up. And then the tube is in the state that they hope to keep it in until the tubes can be recovered and come back on a future mission and be examined. So at the end of the crater floor campaign, oh, wait a minute, partway through the Delta Front campaign, this is what the first 10 or 12 cores looked like. And the left of each trio is the abrasion patch, which is 50 millimeters across. And then the pictures looking in at the end of the tube, one each for each of the two samples that were collected at each of these places. And here I've matched up the diameter of the end of the core is the diameter of the end of the core. Okay, 13 millimeters, that's the inside diameter of the tubes. They also want to collect some regolith, the loose dirt on the surface. And so there they find small dunes that they don't have to drive on, or that you don't have to all 6 wheels on them as you go over. And then they have a different drill bit. It's more like a soil bit for drilling soil. And this is collecting 2 regolith samples. So there was a point at which there were 4 pairs of igneous rocks from the crater floor campaign, 3 pairs of sedimentary rocks from the Delta Front campaign. Both of these exhibited evidence in the different spectroscopy images, especially the Raman, and visible and near infrared, that some of the igneous rocks had reacted after they were igneous rocks. They reacted with small amounts of water and formed water-soluble minerals like sulfates and carbonates, maybe clay minerals. The sedimentary rocks pretty much by definition interacted with water, both physically and chemically. In both cases, there are tentative indications in the Raman spectroscopy that there are at least some reduced carbon compounds. The use of the word organic chemistry is a historical confusion of epic dimensions. In the 19th century, every science started as its own thing. You know, chemistry is just alchemy with a balance, with being able to weigh things, right? Just knowing how much of, you know, a pinch of this, how many milligrams, you know, do you need? And reduced carbon compounds with carbon other related bonds were first identified as, hey, this is an organic matter, so we'll call these organic chemistry. These are organic molecules. It doesn't mean an organism produced the most organic molecules, reduced carbon polymerized molecules, form abiotically. They form without the intervention of a life process. But every freshman who's ever come in, right? And I don't blame them. So the spectroscopic evidence exists of such compounds. Doesn't mean they're biogenic. They may be naturally abiogenic. Okay, but life as we know it does have some organic molecules, and if we had if we could use instruments that help us sort them out more and distinguish the relative proportions of different ones, we might be able to sort out the definitely not biotic from the, well, these could have been biotic. and start looking at proportions and stuff. So the likely presence of organics. And once the samples come back, we can use those better instruments on Earth and determine which combinations might indicate biogenic versus abiogenic origins. And then any of these will be materials that the astronauts and their rovers will have to walk on and drive across and live off the land in terms of what resources exist, what hazards exist, dust. The samples will illuminate any of those high priority science objectives. And that's just the ones that were collected in those first batches of tubes. So it was determined, and it again, it's not like, hey, everybody, you know, we have two of everything. Why don't we do this? No. It was understood at the beginning why they were going to do this. It was understood that there was going to be an early batch that as kind of an insurance policy, just in case something goes wrong with the rover later, let's make sure we've left some scientifically useful samples somewhere where they're going to be really easy to get at. And so let's collect a number of the early ones as pairs and then make a choice about which member of each pair gets left behind and which one continues riding along with the rover while the rover keeps adding more samples to the collection. If the rover breaks and can't offload the samples, at least the ones we deposited can be recovered. It's not as complete a set, but it has a variety of rock types that meet quite a number of the scientific objectives, and it would be return worthy. It would be worthy of returning it. So that selection process was implemented by the mission team from samples that were taken all the way over here on the crater floor campaign and the ones from the Delta Front campaign, and were deposited as they drove across it here. Months earlier, they were saying stuff like, "This is the flattest surface on Mars I've ever seen." Yeah, there are little rocks the size of tennis balls and golf balls. No hazard to a rover, no hazard to a future lander. Flat, horizontal, away from cliffs. Right? This would be a great place for a retrieval lander to meet the samples if it had to. And so they got really lucky in the way this crater evolved geologically. So at a region, an area called Three Forks, because it's where three of these canyons kind of point together, come together here, called Three Forks on the crater floor. This was going to be where the depot, where the first cache was going to be depoted. They were starting this in November of last year, and it took them until late January, early February. It took about 3 or 4 days full time for each one. They used Ingenuity, the helicopter, to scout and map exactly where all of the tennis balls and golf balls were, and pick a number of circular areas that would be far enough from another one that the helicopter spreading the dust around on one wouldn't affect the next one over. And they established something like 15 places, and then they chose 10 of them and actually deployed one of each member of those cores. They did it all the same way, just carefully pulled it out of the rack that they live in on the spacecraft and gently dropped it onto the surface. I did hear that the first one did not take advantage of randomness and actually landed on its end and stood up. And so they had to decide that let's knock it over on purpose so that it winds up in the stable geometry. This is one of my favorite pictures in a sense, because one way or the other, we're going to get a collection like this. We're either going to get these 10 samples in their the onboard twins of these samples, or we'll get these. And these are now on the ground, ready to pick up. And people are going to be studying all of the data, the abrasion patch data, the pictures of the ends of the core, everything about these for the next 10 years, preparing for what they'll want to do with them if and when they eventually come back. Oh, did I say 10 years? More about that in a minute. Okay. All right. So the group that I'm part of defined selection criteria. If it's longer or shorter, if it's different in some particular way, which one to leave, if the differences within the pair, apply these criteria and select the one for being left behind. The mission team said, great, thank you for the criteria. They applied them. They found one instance where somebody doing their homework afterwards, remember those couple of bumps outside the one abrasion patch? I told you those bumps would be important. Somebody kept working at that even when the rover was looking at new abrasion patches and looking for new places to drill. And eventually they said, one of these is actually really close to those bumps, one of the cores. And if it got some of the bump material in the drill, that would be an additional thing that the other one didn't have. So let's keep that one on the spacecraft for the cache that we hope will come back with more samples and come back, and pick the other one. Even though it's longer, we'll leave the longer one behind because the slightly shorter one might have this more scientifically more interesting additional feature. Okay. The group that I work on came up with those rules, and we don't have executive authority, but we advise the mission headquarters. And the mission team checks with us, you know, you represent the community, we did this. Is it okay that we changed the rules on this one? We found a special condition. Our rules called for special conditions. If there's a special condition, invoke it. But it's kind of a fun thing to be the one making the rules. Nothing at all like being a professor. This was a notional diagram. They knew where it was going to land. They knew how many tubes it could carry. They knew how far it was going to be able to travel. And approximately what kinds of samples might they expect to get. And they kind of got pretty close. That mafic floor unit, another mafic floor unit, the delta front deposits and regolith. They wound up collecting twice as double of each of these and double of each of these. Half of them stay on board. Double regolith. From here on out, there won't be a second contingency depot. The Three Forks depot is now, is plan B. Plan A is the samples on Perseverance. So the twins that are already there, and any new samples that are being collected one at a time, not two at a time anymore. And if they finish the upper delta and the bathtub ring, then they'll collect more samples, one each. And if the mission is extended farther than that, and they get more money to keep everything going, and the hardware is still functioning, then they get to the crater rim, and outside the crater to all those other kinds of units in the older geologic terrain around Jezero crater. Today is Sol, Mars Day, a little more than 24 hours long, Sol 812 on Mars. The Mars Exploration Program website shows a little red circle with a tube in it. Every place where it collected 2 tubes in the crater floor campaign, 2 tubes in the delta front campaign. And now it's on its way here. It's already collected one more here, a singleton here and a singleton somewhere along here. I know it's collected this one. I think it's collected one up here also. And then it's made it around the end of this big crater here that is younger than the delta, that the impactor came in and made a fairly large hole, about a mile across. Not real big by the standards of such things. All right, so this is kind of where we are. Now, what do we got? We've got the Perseverance rover, which right now has another It's got the 7 partners of the 7 igneous and sedimentary rocks that we left. It's got an 8th tube with the regolith sample in it. It still has some witness tubes for contamination and stuff like that. All of that from the crater floor campaign is that's half of each pair is still on board, plus the 2 sandstones they collected at the beginning of the upper fan, top of the Delta campaign. Those are on board Perseverance. Perseverance is going to collect more samples on the top of the Delta and then make its way to the bathtub ring. The Ingenuity helicopter is way past its warranty. It was designed for something like 10 flights. It's up to 50 now. Right now, all it's doing is flying. It's a little scout. It's a little drone with a camera, and it can scout around and get closer up looks and looks from above at places where the team has to make decisions about, should the rover go here or should the rover go here? And the Ingenuity data are being really, really, really helpful. Let me see what's next here. Oops, that's what's next. Okay. These exist. The plan is, and NASA is really strange, really curious experience to work with them this much. There are plans that are really locked in up to a certain point. And then at that point, when those decisions are made, you still don't know what the next decisions are going to have to be. So you have to build a certain amount of adaptability in, but you do have to finish the engineering. You can't send up a mechanic to add one more thing to the spacecraft. You can't do aftermarket improvements on the instruments. So the activity to do most of the rest is happening on Earth while the mission team is continuing to do what it's been doing. The wide angle views that include where should we go next, the helicopter flights. It's been decided that it's been known for a long time that there will be a sample retrieval lander. This is a future mission that's got to be built and assembled and tested and put on top of a big rocket and launched and arrive at Mars. And if it gets through all of that, then we can talk about actually using it. All right. It will be carrying a different design of the helicopters. It'll have one helicopter. It'll be more capable. It'll be able to carry several kilograms of stuff. Not that it'll have to, but it can, if it needs to, it can pick up the tubes and fly a couple 100 meters with them and bring the tube. If Perseverance blows out a wheel and has to dump the tubes, and this can't land closer to it, or this can't drive up to it, this is stationary, then the fetch helicopter can be used. If everything about Perseverance is working, it will come right up, drop the samples, and the Italian-built, European Space Agency-built robotic arm will pick up the sample and put it into a container that's inside the nose cone of this miniaturized submarine-launched ICBM. It will be on the sample receiving lander. And in order to not have all sorts of debris flying around when it fires, like what happened to that SpaceX ship a month or two ago that actually destroyed its launch pad with its 29 engines, concrete chunks, flew what, 1.6 miles? The launching of this is going to be just as cool as out of a nuclear missile sub. The engines don't fire on those until after they're above water. They're ejected out of the tube, and then the engine ignites. This is going to be, I don't know if it's spring loaded or what, ignite. Okay, there are several technologies that have to be refined considerably before there is confidence in making that work. It contains about a basketball-sized object that holds 30 tubes. There are 30 seats on the bus for tubes to come back. And so the mission team now has on board the 10 parts of pairs that they left at the Three Forks Depot. They have their counterparts, and they can continue collecting more. I think if they get all the way through all the tubes and fill them, they'll have 3 more tubes than they can bring back. And so then there will have to be workshops and criteria established to decide which ones are we going to leave behind. And after relative scientific priority, whatever. Oh my gosh. Oh, this is divine intervention. That's what this is. This is why you're going to get home before midnight. In the meantime, all this, I really like this spacecraft. The Mars Ascent Vehicle, MAV. Those are my initials. MAV is going to bring the samples off the surface of Mars. I love it. I'm going to be there vicariously. You know, this is going to take the sample, the orbiting sample container, into low Mars orbit and jettison it from the front of the spacecraft, where an automated rendezvous will happen with what will be the largest dimensionally planetary spacecraft ever flown, the European Space Agency Sample Return Orbiter. It's going to be launched from Earth in 2027 under the current schedule, and will be in orbit before this is launched from Earth in 2028, and ready in orbit to do communications relay and so forth, and will automatically, autonomously intercept the orbiting sample container, process it, seal it up in the Earth return vehicle. And then it will also have the largest ion drive that's ever been put on a spacecraft. So it will have ion drive on the way out. And once it has the orbiting sample, it'll have the ion drive on the way back, where it will take the encased sample and let it enter Earth the way other missions have. There are, all of these are works in progress right now. All right, time is, it's not total crunch time yet, but for something that has to be ready for launch in 2027, or ready for launch in 2028, there's no time like the present.
Yeah.
You know, to be as well prepared as we can be and as far along as we can be. I'm a scientist, I'm not an engineer. So the only time our committee gets asked for things is when the engineers say, how much can we heat up, you know, sealing up the orbiting sample. So, so it's total break of contact between Mars and Earth. Seal it up perfectly with multiple layers of sealing it up. You know, how do you weld it, braze it? Oh, that's going to heat things up. How much can we heat the samples up without ruining something that has to be measured? That's our job. Our job is to respond to, you know, headquarters says, the engineers are asking for a waiver of the temperature for short term. How much can the samples tolerate? So we have to, there's a design limit that nothing that the mission does should allow the samples to ever exceed 30 degrees centigrade. That's the maximum temperature on a hot summer day at this site on Mars. Very seldom that hot, but at least once in a while, the samples would already have experienced that naturally anyway. So there's no point in engineering something to keep them at 20 below because they've already been 10 above. But that's one of the kinds of things that we have to do. The end game of all of this, and I've been involved in the workshops and stuff like this for about 15 years now, and I more and more frequently until getting like officially involved. And I remember about 10 years ago, the person who runs all these workshops saying, as we were talking about the criteria, what are the contamination requirements? You can't use certain metals in designing any part of the spacecraft if the isotopes of those metals are something the scientists want to study when the samples come back. Okay. The contamination requirements, we came up with those in a different subgroup of us at just a town hall meeting came up with those, the inorganic contamination standards in 2014. It was one of the, because that they hadn't started building stuff yet. They had to select what they were going to make stuff from. But at one of those meetings, 2014, 2015, somewhere in there, the guy in charge of this said, look, remember, there we go. Oh, well, you don't get to see the last picture. Too bad. Remember, we're doing this. We're establishing the design requirements in order to support getting samples back. And they will be examined by people who aren't us. I am in my late 60s. The samples, if everything leaves the Earth as planned, the earliest the samples could be brought back would be 2033, about 10 years from now. I'll be in my mid-70s at that point. I'll be happy if I'm around, and I'll be happy if they'll wheel me into the visitor center to look at stuff or whatever. The last slide that I could plug it in is me at a transmission electron microscope looking at samples from the Stardust mission, which I did get to do, comet dust from Stardust. The transmission electron microscope is 4 feet taller than I am, and it weighs a ton. It's too big to put it on a spacecraft. And there are many analytical functions in a transmission microscope. Nowadays there's nanometer scale spot size secondary ion mass spectroscopy. Those are also hundreds of kilograms and many square feet of lab bench space. None of these instruments tolerate vibration at all well in doing the work that they do. This is the precision of the spot size. When I was at the Smithsonian, there was a scanning electron microscope on the 3rd or 4th floor, the floor our department was on. When there were vibrations in the walls because of the air handling or anything, the vibrating of the walls vibrated the air in the room just enough that you could see wiggles in the pictures. All right. Usually these are built in basements, and the foundation is cut around them, so there's no continuity of sound waves through the concrete. You actually build a moat around them so that the vibrations elsewhere in the building don't affect the foundation. And they have all the acoustic tile, egg carton foam to minimize vibration in the air. You can't fly those things. There's no way you could put that on a spacecraft. You couldn't put it on an International Space Station. The service contracts are mind-blowingly expensive. I've been at the Smithsonian watching one technician have to live, a factory tech, from the Boston office of the person that made the instrument, have to live in the DC area for 6 weeks to get the instrument running again. We can't have something that is that delicate. It's fantastic when it runs, and on Earth, we can support the maintenance of those instruments. We can't miniaturize them yet. We can't design them. All of those kinds of capabilities are among the main reasons for bringing samples back, even if they're little tiny amounts of sample. There are so many things at smaller scale and smaller detection limits that we can do in labs on Earth that won't be possible to do in a lab on the surface of Mars or on a space station or anything like that for decades. But in an Earth lab, we can do all this stuff now if we can just get the samples back. Yeah. And that's what we're working at. Thank you very much.
Questions? Folks can hear you at home. Wait for the microphone. Go.
Thank you.
So are you a fan of the Kim Stanley Robinson Mars trilogy?
Yes, I am. Doesn't mean he's right about everything, but yeah, absolutely. In the interest of brevity, let's see. Brevity. Excuse me a second here. Yeah, as far as I can tell, I did this in what, 40 minutes? 35, 45? Little over an hour, okay. Well, it's a lot less than last time. Anyway, I usually open with a slide from page 3 of Red Mars. So yeah, I'm a great fan. And anything particular that you encourage fandom of?
We did that 9 years ago.
Yeah, that was the opening slide 9 years ago.
Because I read the minutes.
Yep.
Today.
Yeah.
Any other questions?
He's wrong about quartz. He has two places where there's something in the there are little bits of quartz on Mars, but not like on Earth. It's just not a common thing. So
Have you found any kind of like resources to build structures or anything like that to help you out, or?
funny you should ask. I fell in with a civil engineer at MSU, a new faculty member, who's actually, okay, so you saw regolith, the powdery stuff. Saw 1 or 2 slides of that. In order to design future hardware to use regolith, there are some minerals likely to be in the Mars regolith that have OH in their crystal structure. If you heat them up to 600 to 900 degrees, you can drive off the OH as H2O. It'll pick up one of the oxygens from the rest of it. The clay minerals are like that. If you heat them up enough, you will evolve. It'll recrystallize into something with no H in it and fewer O's. And some of the H's and the O's will evolve at those temperatures as vapor, which you can condense and use. It's not the only way or even the best way of getting water, but it's one way. There's regolith all over the place. And regolith on Mars has at least some amounts of clay minerals in them. So there's a prospective resource. The engineer that I'm working with has a big grant from NASA to study lunar regolith and Mars regolith for whether any of it can be feedstock for making cement. And there are natural materials that are analogous in some ways to Mars regolith. And there are ways of mixing together, minerals that you bought from the supplier in the right proportions and having something that is a reasonably good simulant of the regolith. And so he's buying tens of kilograms of lunar regolith simulant and Mars regolith simulant and doing all the ASTM standards treatments, trying to demonstrate which of these simulants that are designed to resemble certain reasonably well-known remotely from remote knowledge materials. So on the civil engineering side, the cement and for structures and pavements, we're characterizing the feedstock for him with our microscopy work in a seminar that I run. The MOXIE instrument package that's on the rover is designed to take in Mars atmosphere, which is really thin and mostly carbon dioxide, and break it down to carbon monoxide and oxygen and get molecular oxygen out. It would be a lot cheaper in the long run to use things. The engineer isn't sure there's enough ability to capture solar energy at a high enough concentration per unit area, but the talk has always been, well, on the moon in particular, you have sort of unlimited solar energy. You got no atmosphere doing anything to the moon. So the energy that you could convert to, in the case of the moon, reducing titanium in its 4+ state down to metallic titanium, and a byproduct would be molecular oxygen. So you could make titanium metal and air to breathe. And it would be a lot cheaper to get the air out of local materials, to get the oxygen out that you could use as air in local materials. And gosh, wouldn't that be great if it were a byproduct of, processing titanium and getting metal out of it. So I know that such work, there's at least as much work, by which I mean a lot, at least as much work going on in breathable gases, structural materials, extracting water extracting other valuable volatiles and capturing them. There's at least as many research teams and engineering departments and stuff all around the world trying to figure out how to extract things we need, ideally way more cheaply by using local source materials. Because the cost per kilogram of launching something from Earth that far is a lot. And if it can be, if it can be, sorry?
Somebody at home has a question.
Can you hear me?
Yes, I can. Thank you.
Can you hear me?
Yes, go ahead.
Okay, great. I have two questions, actually. One, what has that article by Dr. McKay been discredited? Alan Hill's 8400 001 in the 90s that came out that, you know, he found microbial fossil, you know, life in the meteorite. Can you comment on that, please?
I can. Can I hear your second question first, please?
Okay. Second question is, you mentioned you work with meteorites too, and I collect meteorites too. I have a Zagami Shergatite here, and the one thing that bothered me about Zagami was that it wasn't red. It was this, you know, whitish grayish color. And then I was so happy to see the cores, all the drill cores from various sites all looked like this. So that was good to know that, you know, that Mars, I guess it's only skin deep, the red, you know, the red part. And not only that, but, you know, Zagami's 1.3 billion years, very young, and the mescalinite glass contains trapped, you know, Martian atmosphere is determined by the Viking, you know, so it's not just the color, but I just love this meteorite, and if you can comment on that. So those are the two questions, Doc.
Thank you. Thank you. Let me do the second question first.
Okay.
If you, and any of you can do this, I'm responding to the questioner, but try this out. How many of you are familiar with the website called the NASA Planetary Photojournal? Check it out. Every image that's ever been in a press release is archived there with the caption that it was given at the time. Now, depending on the reason for the press conference, it may or may not have been the final interpreted results the way it showed up in a journal paper. But whatever the press result was. For the Mars Science Laboratory mission, rover Curiosity, they have drilled 36 holes, not to get cores, but to get powder to put in onboard instruments, to do various analyses with the onboard instruments. And they've made a kind of a high school yearbook picture of all 36 of the piles of powder outside the hole. And about 2/3 of them, a little more than 2/3 of them are red, meaning that even when you crushed up the material you were crushing up crushed into particles that were still red. The red pigment is there. However, the other third are gray, like grinding up any rock into a gray powder, as the questioner was referring to for Zagami. And the point about Mars, the red planet, and the red being skin deep that the questioner just raised is not only is it exactly right, but it was a big revelation to me. I spent part of my life studying Earth's red bed sandstones, only to realize that only a few. The thing with Curiosity, finding 2/3 of them being red, okay, there's one thing. Curiosity was sent to a place specifically to look for sedimentary rocks. So I'm not surprised that they found some red beds among the sedimentary rocks. What I was surprised by was how many they found that weren't. The 1/3 that weren't red beds, that just they crush up gray. So the Mars is the red planet because of the dust. It's that couple microns of dust that gets redistributed by the hemispheric scale dust storms every warm season in the right hemisphere. That gets redistributed and it makes the whole surface look red. The planet itself, if you could get rid of the dust, much of the surface would be gray. like the little piles of gray powder around these various drill cores. So those are my comments in response to the voice from above there. The McKay and others 1996 paper about Allen Hills, that's another talk. I have the slides, but has it been discredited? There's a kind of a philosophy of science, a kind of a scientific logic question. How does one, if you have one observation and you can explain it, you know, A, B, C, D, you can explain it 4 different ways. And you can somehow disprove 3 of them. You can falsify those hypotheses. Then, as you know, Arthur Conan Doyle made Sherlock Holmes say, if once you've tried everything else and falsified it, whatever's left must be what it is. There's actually a logic problem there too, if you think about it. But what McKay and others said in their paper, in the 1996 paper, they said something to the effect that it could be that each of the 4 observations they had polycyclic or aromatic hydrocarbons, one particular kind of organic molecule. They had little carbonate globs with oxidation reduction chemistry in the carbonate minerals. They had magnetite, which is a form of an iron mineral that has both oxidized and reduced iron in it, ferrous and ferric iron. Fe3O4, 2/3 of those, or one of them. It's a mixed oxidation state mineral, so it's not entirely oxidizing. It's not like hematite, not like rust. It also tells us something about oxidation reduction conditions. And then, like the last line of evidence was these little things in the microscope that looked like bugs, looked like microbes, or nanobes. They were too small to be microbes. And of course, we're visual. That's why we put chemical data on graphs, so we can see the chemical data. So we're visual, and a lot of people got attracted to the microbes, the putative microbes. And McKay and others said there are abiotic origins that are possible for each of these individually. But the explanation for making one abiotically would be a different explanation than making the second one abiotically, and a different one than the third one, and the third different one than the fourth one. And so invoking what was basically Occam's razor, when faced with a range of complexity of choices, choose the simplest one. Nature doesn't have to be simple. It's just the human mind prefers simplicity, right? The application of Occam's razor is a human decision about how to think about complex things. It imposes no requirements that nature actually behave that way. All right, but let's apply, we're human doing science, so let's apply Occam's razor. And what McKay and others suggested was the simplest solution is that they all form by the same process, instead of explaining each of them separately by 4 unrelated processes. Now, I don't know how one formalizes the logic of that. What wound up happening was each of the 4 lines of argument was just destroyed, you know, by the intellectual equivalent of heavy artillery fire. Each by groups of specialists. Oh, the carbonates could have formed at 800 degrees. Oh, the PAH is the polycyclic aromatic hydrocarbons. They could form some other way. Magnetite, and I wasn't one of the first people to demonstrate this, but we've seen it in our own work. The little things that look like microbes in their pictures are a consequence of the way the samples were prepared. Everything you put into an electron microscope, if it's not made of a conductive material, you have to put a conductive coating on it so the electrons don't build up and just negative repels negative and just rejects the electron beam and you can't take a picture anymore. You have to conduct electrons away, put a conductive coating on. And because they were using an unusually, well, it was a new kind of scanning electron microscope with a new emitter And no one had ever looked at anything that could get magnifications and spatial resolutions that good. And no one realized that the coating itself has a texture if you look at it small enough. And the coatings clump up around the edges of things. So if there are irregularities on the surface, you can wind up having things that look like microbes all lined up with each other, or if it's a flaky clay material with edges in different random orientations, then you get microbe things looking like they're different, you know, in different orientations. And yeah, they kind of look a little bit like, you know, sausage-shaped microbes, but you can form them by how you prepare your sample. You can do that. So the dilemma that we all have is so what do we do, you know, with that McKay and others idea? Has it been discredited? Oh, is this still being recorded? Okay, well, all right. I'm already. I'm one of the rare people I think who would like to treat people on both sides respectfully and civilly. This episode really polarized the community a lot. I don't want to go into what I know about that now. Nothing homicidal or anything like that, but it you know, it became by the next decade after that paper came out, it became an issue that really divided the community, and you know, groups of people stopped talking to each other. You know, like kind of like the Civil War. You know, two people in the same family, you know, fighting on different sides or whatever. It's hard to say that. I can't speak to how other people's relationships have been restored or not since then. I can't say anything about that. I don't know. Now, but now that astrobiology is a thing, you know, it's its own subdiscipline, a lot of people have been thinking about this kind of stuff and are putting together sort of documents about, all right, so we don't have that big blow up next time. You know, what criteria should we use and how should we address them and how should we get the word out about them and stuff? And I have a slide in the talk I give on this that shows a quote from McKay and others and a quote from what we think we should do in the future. And it says the same thing about combinations of things are going to be more persuasive than individual things. So I don't, the community, and I don't work on this. I work on the meteorites. I never even had high school biology. All right. So I don't do anything with the microbial side of things, but I can read. And it says something to me that whole groups of multi-generations of thoughtful people trying to come up with what combination of things would we look for and how what's the acceptance threshold for this idea? What makes it convincing? Can you quantify convincing versus compelling or persuasive or suggestive or, you know, as a conclusion for a line of argument? But it strikes me that they have workshops and hundreds of people help write these reports, and they really haven't gotten anywhere different than what McKay and others said.
Oh, I thought of another question. What about the new one, Black Beauty?
We've got to call it there. It's 11 o'clock, so we need to go ahead and take our snack break and move on. So
Yep.
we could be here all night. So thank you very much.
Thank you, Rich. Thank
Before
you.
you go, I wanted to give you a
Oh, this is so cool.
I don't think you got one of those.
I did not.
I don't think we did that 9 years ago.
Thank you. Thank you very much.
You're very welcome. Thanks again. All right, welcome back to the masses here that decided to stay with us. Bunch of deadbeats had to take off, but we'll let them have it later. So let's book through the rest of the agenda here. There's not a whole lot to cover. Did anyone want to share any quick observing or imaging reports? Any escapades of going out under the night sky or even the daytime sky?
Venus is the brightest.
Venus is bright. That's right.
He already left, but Eric was doing anything last night on Hive and whatever.
Oh.
Yeah, so if it is clear after we get out of here, I was gonna bring my binoculars. Oh, thank you. And look at Mars and the Beehive. Figured that'd be kind of a nice little bonus for the talk here tonight, but I forgot to bring my binoculars. I carry too much stuff with me to these meetings anyway. But once you get home, you know, be sure to get out your wide field telescope or binoculars and check out Mars and the Beehive if it's clear. So not too many observing and imaging reports. So let's go ahead and move on to astronomical news. There's just a few things I'll mention. Oh, I was going to fire up the computer for this, but now I'm not going to. Kevin Jung, who still sort of maintains our Facebook page along with Jeremiah. Kevin posted something on our main Facebook page, not the group one, but the main one, about Oceanside Photo and Telescope, you know, in Oceanside, California. They're going out of business. Whoa. And I told Kevin that, I told Jeremiah to take it down because I thought it was him. He was like, no, it wasn't me. So I just asked him to take it down. And plus I heard from Jeremiah, you know, he's given them money for stuff he'll probably never get. And it sounds like he's had a difficult time even getting in touch with them to get his money back. So I think it's good we took the post down from Facebook anyway. So none of our members try to order something off their website. But even if you go to their, you know, their brand new 75mm refractor, that Petzl refractor, if you click on that, it goes to a 404 page, say, nope, sorry, not found. So, you know, last time I checked when the website was fully functional, they said they had those in stock and now it goes to a 404 page. So that's not good. But Kevin mentioned, he never supplied a link, but they're doing an auction for all the stuff they're giving away, but it's not as good as it sounds because if you got the Sky and Telescope email today, they always send out their kind of weekly email newsletter on Friday, and it came just before I was packing up to come here. And so they had a little ad, which is what I was going to bring up for an auction, you know, for that. It doesn't mention OPT specifically, but that's obviously what it is because they said they got millions of dollars of inventory that they're going to auction off. But the catch is you have to be there to pick stuff up. They're not going to ship it to you. So it's mainly for vendors that'll probably fly in, bid on it for their stock, not for, you know, maybe some people, some amateur community will go out there, but it's pretty much for vendors, I think. So OPT's gone. We've given them a lot of money. I'm glad we don't have anything pending with them right now, but you know, pretty much all the main stuff that we got for the remote telescope and the Ashby telescope and observatory, we bought that from OPT, but they're going bye-bye. But that reminds me, some of you may not remember these people, but some of us might remember Pocono Mountain Optics, because when I didn't order stuff from Riders at cost when I worked there, I ordered stuff from Pocono Mountain because they're in Pennsylvania, so you could get stuff faster than you could from California. And it's been so long, probably a good 20 years. Something similar happened with them too when they went out of business as people lost money and that sort of thing. So it happens. I did see that the Hubble Space Telescope detected a possible intermediate mass black hole in M4. So I figured every time next time someone takes a look at M4 and Scorpius, you can try to look for a little black hole. Now that you know it's there, it's obvious, right? No, but some of you might not be familiar with intermediate mass black hole. You know, there's the stellar mass black holes that could be anywhere between 3 and 20 solar masses, maybe more in rare cases, but usually between 3 and 20 solar masses from a single massive star's core that collapses. Then there's the supermassive black holes that are millions or billions of solar masses. And of course, there's nothing in the middle. So many have long theorized of intermediate mass black holes that could be, you know, hundreds or tens of thousands or maybe hundreds of thousands of solar masses that fill the gap. And we think globular clusters mainly have those, maybe some dwarf galaxies, but the focus has been on globular clusters. And, you know, it's, for all of these clusters, it's still really circumstantial whether or not it is a intermediate mass black hole and not just a bunch of black holes or a bunch of cluster stars in the center. But this one in M4 is supposed to be around 800 solar masses, which is, I think, the lowest mass intermediate mass black hole I've ever heard of, if it exists at all. And of course, they measured that by the motions of stars in the center. So there's that. And then I just saw the other day that the James Webb Space Telescope observed the giant plume erupting from Enceladus. You know, Cassini made that moon fairly famous. The plume was about 6,000 miles long, which is enough to stretch from Ireland to Japan. So that's a pretty big plume for just a little bitty moon. So I mentioned both Hubble and Webb. Anybody else have any news for the tens of thousands of people we still have here?
Yeah.
Dave?
I read an article, Betelgeuse got 50% brighter here again and possibly go supernova in 2,000 or 3,000 years.
No, I haven't heard that.
I just read an article on that the other day.
Huh. I figured Betelgeuse is kind of unobservable right now, but I'm not sure. Maybe 4 in the morning.
That's just an article I read.
Jack?
NASA, I think since the Artemis crew launch in July, they've postponed or whatever. They're holding off on that for a variety of reasons. And they're launching a supply mission tomorrow up to the space station. And part of what they're taking is a couple of new solar panels. Because a lot of the solar panels that have been originals aren't putting out the voltage and current that they need to. The newer panels are much more efficient. And so they've already replaced a bunch of them in last year or so. And they're taking some more up tomorrow to do some more replacement.
I saw the Boeing launch got postponed too.
Maybe that's the one I'm thinking of. That was the July one.
Yeah, that's all.
Yeah, that's the one I'm thinking of.
Yeah.
I misspoke, but it wasn't.
I don't know what they call Starliner.
Yeah.
It's been back for a while, so. And then instead of tentative, 30 days later, it's like just, definitely postponed. I don't know what that means.
What's the Blue Origin that just packed their bags and said they're not gonna do anything anymore? Is the other one? Bezos or the other one?
Bezos just got the contract for the new lunar lander.
Okay, so
I
wasn't it?
think he's failing on Blue Origin's going with the lander now. They're just deciding on to do.
One of the 3 companies that have been launching and trying to says, yeah, we're done. We're out of here. We're not gonna do it anymore.
I thought it'd be really easy for them, but obviously not. Space flight is hard.
They didn't have enough
I can't imagine why.
They didn't hire enough the ex-NASA.
Yeah.
So-
Blue Origin, little sub-article things. It just wasn't making money. But when they got the contract with the lander, I think that's when they said, okay, we can pay all of this. The lander's gonna be carried up by somebody else.
All right, any more news? Okay, let's go ahead and move on. Let me just go through the events coming up. I'm going to do pretty much the whole summer because we are not going to meet, until September because, well, for like a regular type meeting because we're not going to have a meeting in July because most members don't care. Of course, most members don't care today, but we'll work on that. We're still getting past COVID, so I'm still trying to cut people slack here. Then we'll have our picnic in August, and then we're going to be at the Nature Center in September. And we got some loser giving the feature presentation. I can't remember his name. The guys are real. We decided to have him out of pity anyway.
No respect.
All right, so we have public observing sessions on June 10th and 24th. Hopefully we'll have our first good one coming up here because we haven't had a good one yet.
Yep.
I probably should have let the last one go, but it just didn't look good. It was the way I thought the first session was going to go. I thought the first session was going to have the sucker hole, but it was nothing but clouds. And I thought it was going to be mainly clouds last week, but it turned out to be, we could at least observe the moon for a little while, but oh well, whatever. It is hard to judge the weather. And we got more public observing sessions in July. The sessions on July 8th and 22nd are pretty much our only club events for that month. And then we got public observing sessions on August 12th and 26th. The one on August 12th will focus on the Perseid meteor shower. So bring out a reclining lawn chair and blanket and prepare to look for Perseids. And for those of you that want to get to some dark skies and do some observing and astrophotography, you can join us at the Garden Getaway. in the Huron Manistee National Forest. That'll be roughly between August 16th and 20th. Unless Dave says you can come earlier and stay later, or he just kicks you out early. It's totally up to him, but you'll definitely have a few good days there. And if you haven't been there, it's dark. Just be prepared for dew, lots and lots of dew. Because that one good night was really dewy.
Oh.
Prime focus. I just wanted to thank, of course, Dave Garden for his article on restoring the Ashby telescope. Hopefully, we'll get a chance to look at it here soon. And Joe Comiskey had that great article on sketching. I've been wanting an article on sketching for a long time, so I'm glad Joe put that together. And the sketches were really nice too. So if you haven't taken a look at the June 2023 issue, be sure you check out those two articles because those were great. And we got a nice observing report from Don again. So keep the submissions coming. It's been making the newsletter, I think, pretty lively lately.
Richard, I am working on an article for the project.
Great.
I have kind of roughed out but I'm in the process of trying to figure out the fundraising part of that.
Yeah.
So there will be a request for funds and that.
Just say send check here.
Check here, address it to this, and on the memo, put this on. And here, money goes to the right place.
And say if you don't give me money, I'm not letting you in Kamsey.
Oh, I'm sorry, I forgot about the meeting on Friday. I just happened to be up here, but I just forgot to unlock the door.
No, I just make you turn people away. Don't turn me away. Huh? Of course, I got no money to give. I'm poor. So as usual, the deadline is the 15th of every month. And that's pretty much it. Any other items anybody wanted to talk about? Sounds like a big negatory. So as mentioned, August 5th, we will be at Van Buren State Park for the, gosh, where are we? I should have noted what number this is, but it's up in the 20s. So it's the 23rd, 24th, 25th annual Perseid Potluck Picnic. And again, I'm really hoping the weather's better this year so we can not be chilly and have plentiful sunlight where we can at least look at the sun, or at least not be cloudy and gray and depressing like it was last year. So we're hoping, and no way that can happen 2 years in a row. So I think we're in good shape. So without further ado, it's about the same time we got done last month, so that's not too bad. We'll see you next time. So have a great summer and just be sure to come out for observing.
Yeah.